Today we'll delve deeper into the study of a phenomenon that is both violent and vital in the grand cosmic plan: the collision of planets. The cataclysms in which planets collide and merge are not just spectacular shows of cosmic fireworks. They are the architects of worlds, the creators of moons, and perhaps the creators of life itself. It is here, amidst the chaos of colliding worlds, that we find the solution to our planet's past and the mysteries of other solar systems. Our story begins about 4.5 billion years ago, with the colossal impact that gave birth to the Earth and its faithful companion, the Moon. Imagine two similar planets in the same orbit, pulled together in a cosmic embrace. This grand collision not only formed the Earth-Moon system, but also set a precedent for understanding the formation of planets in the universe. Recent astronomical observations thousands of light years away have recorded a similar but much more dramatic event. Two giant planets like Neptune collided at astonishing speeds. This collision was so powerful that it caused the light of their own star to be attenuated by a staggering 95%. Such observations make new adjustments to our understanding of cosmic events and indicate that planet collisions may be far more common than previously thought. From the birth of satellites to the mysteries of planet formation, today we'll witness the power of gravitational entrapment, unravel the history of our Earth and Moon, and look into the future of space exploration. Across the vastness of the universe, the birth of satellites is a tale of cosmic creativity. Satellites, or moons as we often call them, are born in many different ways, each telling a unique story of celestial mechanics and cosmic chance. One of the main ways in which satellite formation occurs is within the circumplanetary disk. This disk, composed of gas, dust, and debris, orbits around young planets like a miniature solar system. Over time, the material in this disk coalesces, giving birth to moons. The classic example is Jupiter's Galilean moons, Io, Europa, Ganymede, and Callisto. These moons form from the same disk that surround Jupiter when it was young, a process mirrored in miniature throughout our solar system. Another intriguing challenge is gravitational entrapment. This event occurs when a wandering celestial body, attracted by a planet's gravity, becomes trapped in its orbit. Neptune's moon Triton is a prime example of this. Astronomers believe that Triton, with its retrograde orbit, was captured by Neptune's gravity, and now the interplanetary vagabond is locked in endless tandem with its host planet. Finally, we explore the third, a violent but creative process resulting from the collision of giant planets. This scenario resembles a celestial race for survival, where the consequences of such colossal collisions can lead to the formation of moons. The origin story of our own moon is believed by many scientists to be the result of such a cataclysm. About 4.5 billion years ago, a Mars-sized body called Theia collided with the young Earth. The debris from this massive collision eventually coalesced to form the Moon, our permanent satellite. Each of these processes, formation in the near-planetary disk, gravitational entrapment, and the consequences of planet collisions, provide evidence for the dynamic and often tumultuous history of planet formation. Let's take a closer look at the thrilling spectacle of gravitational entrapment. The very process when a celestial wanderer drifting in space is captured by the gravitational pull of a planet, changing its fate forever. One of the most intriguing examples of this cosmic phenomenon is Neptune's largest moon, Triton. Unlike most moons in our solar system, Triton orbits Neptune in a retrograde direction, a clear sign of its dramatic past as a captured object. This unusual moon, with its icy surface and thin atmosphere, was likely a free-floating object in the Kuiper Belt before Neptune's gravity drew it into orbit. The Kuiper Belt is the region of the solar system beyond the orbit of Neptune. Although the Kuiper Belt is similar to the asteroid belt, it's about 20 times wider and 10 times more massive than the latter. The secrets of Triton's capture are not limited to its orbit. The event had a profound effect on both Triton and Neptune itself. The capture resulted in enormous tidal forces that altered Triton's internal structure and may have given rise to its geologic activity. In addition, it may have altered Neptune's orbit and axis of rotation. Capturing Triton is not only the story of the Moon, but also a window into the composition and evolution of celestial bodies in the outer solar system. By studying Triton, scientists can gain insight into the composition and characteristics of other Kuiper Belt objects. Its icy surface, with its nitrogen geysers and thin atmosphere, provides insight into conditions in this distant region of our system. The implications of Triton's capture extend to our understanding of planetary systems beyond our own. Such events can dramatically change the dynamics of a planet's moons and rings. This shapes our understanding of how satellite systems evolve and influences the search for similar phenomena in exoplanetary systems. Now let's move closer. As we've already mentioned, the Earth holds the secret of a turbulent and pivotal past, a secret it shares with its closest celestial partner, the Moon. The story of their birth is a story of cataclysm and creation, which determined the fate of both bodies as a result of a monumental event, the collision of planets. According to the giant impact hypothesis, about 4.5 billion years ago, a Mars-sized body called Theia collided with the young Earth. This colossal impact was not just an impact, but a catastrophe whose energy was enough to melt and vaporize both Theia and much of Earth. After this cosmic cataclysm, a disk of debris consisting of parts of Theia and Earth revolved around the molten planet. Over time, these fragments fused together under the force of gravity, giving birth to our Moon. The Earth, too, was forever changed. Its composition, axis, and orbit were altered by this collision. The evidence supporting this hypothesis lies not only in theoretical models, but also in tangible evidence. Samples of lunar rocks brought back by the Apollo mission are strikingly similar in composition to Earth's mantle, suggesting a common origin. In addition, computer modeling of this event accurately matches the current orbital dynamics of the Earth-Moon system. This theory has profound implications for understanding the history of the Earth itself. The impact probably played a crucial role in shaping the planet's geology and probably even its ability to harbor life. By stripping the Earth of some of its primordial atmosphere and altering its rotation, the impact may have laid the groundwork for the unique conditions that support life as we know it. Thus, when we look at the Moon, we are looking not just at a satellite of the Earth, but at a part of our planet's past, a celestial body born out of one of the most dramatic events, at least to us, in the history of our solar system. Among the accounts of the formation and evolution of our cosmic neighbor are other, often overlooked consequences of planetary collisions. These events not only shape the planets and their moons, but also leave behind characteristics and phenomena that further define the character of these celestial bodies. One such consequence is the formation of planetary rings. These beautiful and delicate structures that often adorn gas giants such as Saturn may be the result of collisions. These rings, although not formed directly from a single massive collision, are believed to be the remnants of smaller and more numerous events, from tiny ice particles to large chunks of rock orbiting Saturn. These bodies create the iconic appearance that we see today. Such rings are not unique to Saturn. They are a common consequence of collisions in planetary systems. Another intriguing result is the tilt of the planet. Uranus, with its peculiar axis of rotation, is a prime example. Astronomers suggest that a massive collision with an Earth-sized object in the distant past may have flipped the planet on its side, resulting in its extreme axial tilt of about 98 degrees. This tilt accounts for the planet's incredibly contrasting seasons and unusual magnetic field. Coming closer to home, Mars presents another intriguing case study. The Borealis Basin, a huge impact crater that occupies most of Mars' northern hemisphere, is thought to be the result of a colossal impact. The red planet also has a smooth, flat northern hemisphere, in stark contrast to the heavily cratered southern hemisphere. The dichotomy suggests that a powerful impact occurred in Mars' past, altering its surface and possibly also affecting its internal dynamics and subsequently the planet's climate and atmosphere. Even Venus, our sister planet, bears traces of a history of collisions. Its dense atmosphere, composed mostly of carbon dioxide with thick sulfuric acid clouds, raises questions about its past. Some theories suggest that comet impacts may have contributed to the dense atmosphere by delivering volatile compounds. These events may have created the greenhouse effect on Venus that led to the current inhospitable conditions. Each of these examples once again convinces us that even on such giant scales, collisions are far from rare. They continue to shape the physical characteristics, atmospheres, and even climate of planets, leaving an indelible legacy in their evolution. In the relentless pursuit of understanding the universe, astronomers have quite recently captured an amazing event: the potential collision of two giant planets. This unusual observation not only strikes our imagination, but also provides insight into the dynamics of planet formation and the evolution of stellar systems. Late last year, astronomers investigated observations made in 2021, an unusual phenomenon around the young star ASASSN-21QJ. This star, located about 1,850 light-years away, showed all the signs of such a grand event. The evidence? Significant infrared brightening and complex optical eclipse indicate a colossal planetary collision. The infrared enhancement of the star, corresponding to a blackbody temperature of 1,000 Kelvin and lasting about 2.5 years, was superimposed on a wavelength-dependent optical eclipse lasting about 600 days. These observations led researchers to hypothesize the collision of two exoplanets, each with masses ranging from a few to tens of Earth masses, located at a distance of 2 to 16 astronomical units from the star itself. Such a collision is a spectacle of cosmic proportions. Imagine two planets, presumably similar to Neptune, being attracted to each other by gravity and colliding at high speeds. The consequences? A debris cloud that attenuates 95% of the star's light, and an incredibly hot, glowing remnant visible in infrared light. The significance of this event goes far beyond its awe-inspiring visual impact. It provides a glimpse into the rare processes that form young solar systems. These giant collisions, predicted by theories of planet formation, play a crucial role in determining the architecture of planetary systems. The study of ASASSN-21QJ is a testament to the importance of continuous astronomical monitoring. Such observations allow us to record these fleeting but informative events, shedding light on the dynamics of planet collisions and their role in the formation of solar systems. Events occurring during the early and turbulent stages of stellar system evolution play a key role in shaping the characteristics of planets and moons. At the stage of the birth of a star system, space is a crowded, chaotic place. Planets, planetesimals, and debris are in constant motion, often colliding and merging. These collisions can lead to the formation of larger planetary bodies, changing their orbits, composition, and even atmospheres. Take our Earth, for example. Its collision with Theia not only led to the formation of the Moon, but also contributed to the tilt and speed of the Earth's rotation. This impact may have played a crucial role in the formation of Earth's stable climate, which eventually became the basis for life and our existence. The recent observation of the star system ASA SSN-21QJ emphasizes the significance of these events. This colossal collision provided a huge debris cloud. Following this discovery, it becomes more apparent that such events, while dramatic, are not rare anomalies, and at the same time form an integral part of the evolutionary narrative of stellar systems. Planetary collisions can have a variety of consequences. They can strip a planet of its atmosphere or promote its development, affect its magnetic field, and even determine its potential habitability. The moons from these collisions carry the legacy of their parent planets, providing clues about the history and evolution of the systems. Collisions also play a role in the redistribution of materials within the solar system. Elements formed at the heart of stars disperse and recombine, contributing to the diverse compositions of planets and moons. This cosmic recycling is fundamental to understanding the diversity of worlds we observe in our galaxy. We've already moved into a new era in astronomy, and the future of research and discovery in planetary collisions holds great potential. Continued advances in technology and ambitious space missions have the potential to revolutionize our understanding of cosmic events. Current and future research depends heavily on advanced observational technologies. Ground-based telescopes are becoming increasingly powerful and can detect even faint traces of distant collisions. Space telescopes, such as the James Webb Space Telescope, offer unprecedented views of the universe, providing deeper insights into the mysteries of planet formation and destruction. Future missions specifically designed to study exoplanets will further deepen our understanding. The goal of these missions is to obtain direct images of exoplanets, analyze their atmospheres, and even possibly detect evidence of past collisions. The data obtained will provide a better understanding of how planets form and evolve. Along with advances in observations, computational modeling is also undergoing a revolution. Supercomputers are now able to model complex planetary collisions with greater accuracy, helping us to predict and understand the outcomes of these events. These models, supported by real observational data, will play a crucial role in testing and refining our theories. The study of planetary collisions is a global challenge. Collaborative projects and international partnerships play an important role in pooling resources and expertise. Such collaborations not only advance our knowledge, but also inspire future generations of astronomers and scientists. In the grand narrative of the cosmos, planet collisions are far more than just spectacular events. They are the sculptors of worlds, the creator of moons, and shape the very characteristics that make each system, each planet, and you and I so unique.
The solar system is unique because of its special structure and, most importantly, optimal conditions for life to develop. Therefore, missions that are aimed at finding planets we could potentially inhabit and trying to find them in similar star systems. But what if we tell you there is a planetary system not far from us that is very similar to ours? And more to that, it consists largely of planets that are similar to Earth. Today we'll tell you about the TRAPPIST-1 system and whether or not its planets would be able to support life. The TRAPPIST-1 system was discovered very recently. In 2016, a team of scientists led by Michael Guillon and Susan Lederer discovered 3 planets orbiting an ultra-cool dwarf star known as TRAPPIST-1A, 40 light-years, 235 trillion miles, 378 trillion kilometers from Earth. However, the very next year, NASA astronomers made a new discovery using the Spitzer Space Telescope. Turned out there are as many as 7 planets in this planetary system. However, TRAPPIST-1 has no gas giants like Saturn or Jupiter. Almost all of its planets are structurally similar to Earth. These findings led scientists to speculate that perhaps TRAPPIST-1 may have the potential for life to exist there. What does the TRAPPIST-1 system look like? The central star, as we've already mentioned, is a red dwarf. It has 7 planets revolving around it, roughly the size of Earth. All of them have the name TRAPPIST-1, but each planet has an individually assigned alphabetical index from TRAPPIST-1b to H. Unlike our solar system, TRAPPIST-1 has several other important distinguishing features. First, all the planets in this system only face the parent star with one side, the same way as we see the Moon. The time it takes the planets to rotate around their axis is the same amount of time it takes them to orbit the star, which means that one day on these planets is equal to 1 year in length. This process is called tidal locking. It's caused by the gravitational interaction between space objects. Secondly, all the planets are very close to each other. It is likely that the desensification of the system is caused by an internal migration of the planets, which also led to their resonance. For example, the distance between the star and its nearest planet, TRAPPIST-1b, is only 11 million miles. For reference, the average distance between the Sun and Mercury is 36 million miles. This means that these planets might be heated better due to relative proximity to their star as well as interplanetary gravity, which would allow them to retain water inside themselves. Does this figure that all these planets can hypothetically be habitable? Let's try to figure this out. First, let's take a closer look at the central star. TRAPPIST-1A is very cold and small when compared to our Sun, for example. Its surface temperature is only about 4,154 degrees Fahrenheit, whereas the temperature of the Sun is close to 9,930 degrees Fahrenheit. Its size can be compared with Jupiter and its mass approximately 13 times smaller than the Sun's mass. However, red dwarfs burn their hydrogen supply much more slowly, which means they can exist for a very long time, several trillion years, in contrast to the age of stars like the Sun, which is closer to 10 billion. According to research by Adam Bergesser of the University of California, TRAPPIST-1A may be about 7.5 billion years old, which would be considered a relatively young age for such stars. However, if red dwarfs are so cold, how could they heat the entire planetary systems? True, for a long time there was an assumption that red dwarfs were not capable of supporting life, but the discovery of TRAPPIST-1 has changed scientists' view. The peculiarity of the proximity between the planets and the temperature of the star maintain, on average, moderate temperatures in the range from -171 degrees Fahrenheit to 258 degrees Fahrenheit on these planets. Now, what's more, thanks to relatively low temperatures as far as stars go, dwarfs can help conserve water on the planet in their planetary system, even the ones closest to it, and also, interestingly, funnel amino acids and important chemicals through their flares. On the other hand, dwarfs can expose nearby planets to strong UV radiation, creating conditions unsuitable for life. Therefore, let's move on to the planets themselves now and find out how the characteristics of their system affect them and the potential life on them. The first on the list is TRAPPIST-1b. Its radius is 10 times larger than the radius of Earth. Similar to Earth, it's also made of rock, iron, and likely ice. Interestingly, 1b may even contain a small layer of water, about 0.2% of its total mass. although some scientists are inclined to believe that the planet is completely dry and has only oceans of magma. However, the conditions on this planet are far from earthly. Obviously, the proximity to the parent star must result in a very heated surface. Moreover, the gravitational influence from the star may cause strong volcanic activity, heating the surface even more and melting the internal rocks. However, the temperature on 1b is too high even for this. Temperature there reaches 2,156 degrees Fahrenheit, which is 2.5 times higher than on Venus at 860 degrees Fahrenheit. The reason for such temperatures may be the high density and possibly atmosphere in which gas accumulates after volcanic eruptions, which prevents heat from leaving the planet. The next planet, TRAPPIST-1c, is similar in composition to TRAPPIST-1b, but most likely has neither ice nor water. It is the heaviest planet in the entire system, even though it has a smaller radius than 1b. It's also very likely that it has high levels of activity. That's due to the influence of the star and orbital resonance. The exact surface temperature of 1c, it's unknown. The star can heat it up to about 158 degrees Fahrenheit, but the internal activity of the planet is capable of raising the temperature several hundred degrees. However, it will most likely not reach the same temperatures as 1b due to the atmosphere, which is likely less dense. One of the features of 1c is its massive core made of metal, which is almost 1.5 times larger than Earth's. Because of this, its large magnetic field is able to protect the planet from stellar wind, a stream of charged particles that could destroy the atmosphere. However, 1c is unlikely to contain water, and like 1b, the surface heats up significantly due to gases, which makes life on these planets impossible. Next, we have TRAPPIST-1d, one of the smallest planets in the system, with a mass about 3 times smaller than Earth. It's composed of rock and metal, but very likely, like 1b, it must have an ocean, a layer of ice, or a dense atmosphere. And that's according to the theoretical research of its mass and radius. Astronomer Vera Dobos believes that the surface on 1d could be as reflective as the surface of Earth. This means that 1d may have liquid water and a dense atmosphere, which in turn may even contain ozone, which would protect the planet against harmful radiation. Moreover, the scientist also suggests that unlike 1b and 1c, 1d can avoid a mass-scale greenhouse effect, which would greatly increase surface temperatures due to its small mass. However, despite strong evidence, some scientists have other assumptions about the possibility of life on TRAPPIST-1d. Researchers from the University of Washington believe that 1d receives more energy from the star than the more distant planets, and therefore it may be similar to our Venus with a pronounced greenhouse effect like on 1b or 1c. Therefore, life is unlikely to develop there. On the other hand, it may also have some hydrogen in the atmosphere, which would prevent it from overheating. Furthermore, its atmosphere may contain a very little CO2, which would have a negative effect on the emergence of life. In addition, its orbit is almost circular, as in 1d may be heated slightly due to gravity. Finally, due to its small size, the planet may not have a magnetic field. Therefore, the stellar wind could carry away volatile particles from the atmosphere, including water, as it may have happened with Mars. The conditions on 1d are quite controversial, so it requires further research from scientists. But the fourth planet in the TRAPPIST-1 system presents the greatest interest to the scientific world. TRAPPIST-1e is more similar to Earth than other planets in the terms of radius, density, and heat received from the central star. Its orbit is 2.7 million miles away from the star, which results in the planet completing a full revolution in 6 days. Its composition as a whole is very similar to that of 1c. 1e is mainly composed of rock and metal. Does that mean there's no water there, like on 1c? NASA researchers believe that 1e is in a so-called habitable zone, a distance within a planetary system where it's neither too warm nor too cold, which also keeps water in its liquid form. Therefore, it's very likely that 1e may contain water, and in quite large quantities, in fact. Researcher Vera Dobos suggests that an excessive greenhouse effect may not be characteristic for this planet, unlike all the previous planets we've discussed so far. This means that 1E would be able to maintain a moderate temperature, maintaining entire oceans on its surface. Moreover, due to its weight, 1E may have an atmosphere that's not too dense. A group of scientists led by astrophysicist Martin Turbet believes that the atmosphere on 1E may be rich in CO2 and contain almost no hydrogen, preventing the planet from overheating. Additionally, 1E can retain its atmosphere for an extended time despite the impact of the stellar wind, and may therefore create optimal conditions for life. However, the exact mass of 1E has not yet been established. Therefore, just as with 1D, it's difficult to say for sure whether or not there may be water on it. Although scientists largely agree on the presence of an ocean and the planet's potential habitability, some suggest that it may be a homogeneous rocky planet. The following planets, TRAPPIST-1F and 1G, are also presumed to be generally similar in their mass, rocky structure, radius, and density to planet 1E. However, that's where the similarities end. Both planets are at a great distance from the star, one 3.6 million miles away, and the other is 4.3 million miles from the parent star, respectively, also within the habitable zone. However, their surface is not as heated by the red dwarf, and scientists suggest that both of them may be covered with a solid layer of ice. Nonetheless, they may have the same heating potential as 1D from gravitational interaction with the star. That is, despite the very little heat from the star itself, planets can be heated properly from the inside, and therefore they are likely to have a global ocean under the ice. Furthermore, likely due to their high internal temperature, the water on these planets could evaporate, forming a dense atmosphere rich in oxygen. And so it is possible that their surface may not be that cold, but could even be warmer than Earth's. However, according to research by a group of scientists led by Bill Quarles, up to 20% of 1F is made of water. Given its possible internal heating as well as the mass of the planet, likely smaller than that of Earth, scientists believe that water can only exist there in the form of clouds. Equally, 1G also evolved with a lot of water. According to some scientific reports, the depth of its ocean can be 416 miles. Although such ample amounts of water may seem beneficial to life, oceanic evaporation can significantly increase the oxygen pressure in the atmosphere, casting doubt on the possibility of any development of a living organism. Therefore, despite the likely presence of water, the question of the habitability of these planets requires new research focused on their atmosphere. And finally, the seventh planet, TRAPPIST-1H, is the most removed from the star as well as the smallest in the entire system. Unlike all the other planets, 1H may be composed almost entirely of water and is likely to have very little rock in its composition. However, it's likely also that 1H is heated much less than the others. The parent star alone would bring the surface temperature to only about negative 153 degrees Fahrenheit. Furthermore, some scientists suggest that the amount of heat generated by gravity would also be quite low for 1H. However, researcher Kathleen Mant believes that 1H may have a lot of volcanic activity, spewing water instead of lava. That would mean the planet's able to replenish its atmosphere due to the emitted gases. Additionally, the remoteness of 1H allows it to firmly retain its atmosphere, probably consisting of nitrogen and methane like on Triton, since the stellar wind hardly touches it. And yet, even this quality does not speak in favor of life on the planet. It's still very cold and therefore probably cannot sustain water in liquid form. But the question remains, could life hypothetically exist in this TRAPPIST-1 system? The tidal lock is not great for sustaining life because one side of the planet's always scorchingly hot and the other side is freezing cold. However, almost all planets in the system can cope with this drastic difference in temperature, due to their water content and their atmosphere. The heated ocean and atmosphere can transfer heat to the colder zones, maintaining the temperature balance. Nonetheless, only the middle planets, 1D and 1E, meet the criteria to be on the list of potentially habitable planets. 1B and 1C are too hot, and may have lost water due to their gravitational relationship with the star, whereas 1F and 1G and 1H are probably not warm enough due to the weak greenhouse effect, or they're also quite hot. But however, 1D and 1E still require extensive research, since conditions on these planets may turn out to be more similar to Venus, although 1E is very unlikely to fall into that category. In fact, if both planets were covered in ice, they might still be habitable. The TRAPPIST-1 system remains very interesting to all of us. In 2021, NASA sent the James Webb Telescope to the L2 Lagrange point with a view to study TRAPPIST-1 among other things. Therefore, we can expect new data on a distant system very soon, which would reveal more secrets about the origin of our universe and possibly even the origin of life.
Space, the final frontier. A mesmerizing cosmic tapestry of stars, galaxies, and nebulae woven together by the threads of the universe itself. But what happens when we find a breach in this grand design? A place where the cosmic loom seems to have jerked, leaving an almost unfathomable immensity. Nothing. Imagine an area of space so vast and empty that if you traveled at the speed of light, it would take you more than 330 million years to traverse it. That's about 23 times larger than our own Milky Way galaxy. A region is so barren where the average density of galaxies is so strikingly low that it challenges our understanding of cosmic structure. This is not science fiction, but a very real, very mysterious feature of our universe. Welcome to the Great Void, a cosmic mystery, an abyss of darkness beyond the understanding of the universe and its formation. To truly appreciate the significance of our cosmic journey into the void, we must first travel back in time, back when the concept of cosmic voids was just a glimpse into the eyes of astronomers. At the end of the 18th century, a new era of astronomy dawned. With the invention of the telescope, astronomers began to map the cosmos with unprecedented accuracy. Yet, as they mapped the shimmering expanse of the Milky Way, they could hardly imagine the vast cosmic structures that lay beyond their field of view. Let's go back to the 20th century. The advent of modern telescopes and observational techniques has opened up the universe like never before. Astronomers realized that our Milky Way is just one of billions of galaxies scattered throughout an unimaginably vast universe. When the distribution of galaxies was plotted, they began to notice something strange. In some areas, there were far fewer galaxies than expected. These areas, originally thought to be observational anomalies, later became known as cosmic voids. Only in the second half of the 20th century did the concept of cosmic voids begin to gain momentum. In the 1970s and 80s, studies of red shifts, the method used to measure the distance to the galaxies, revealed the large-scale structure of the universe. Galaxies were not scattered randomly, but appeared to form a kind of cosmic web with vast expanses of void between them. Voids. With the advent of digital technology and more powerful telescopes in the late 20th and early 21st centuries, our understanding of these voids has broadened. Sloan digital sky surveys and 2DF redshift studies have produced detailed three-dimensional maps of the universe, revealing the cosmic voids in their entirety. The discovery and exploration of cosmic voids
from the earliest hints of astronomers to today's advanced instruments and methods, represents a fascinating chapter in our quest to understand the universe. Yet despite our progress, these vast realms of nothingness continue to baffle scientists. The Great Void stands as a separate mystery. At the same time as we delve into its mysteries, we can't help but wonder, how did it form? As astronomers look further and more precisely, they discovered an intriguing pattern in the distribution of galaxies. Let's start with the fact that on a large cosmic scale, galaxies are not scattered randomly throughout the universe. Rather, they come together to form complex networks of cosmic structures. These networks, often referred to as the cosmic web, consist of clusters of galaxies, threads connecting these clusters, and vast empty spaces between them. The voids look like vast regions with a much smaller number of galaxies, in stark contrast to the dense clusters and threads of the cosmic web. The realization of the large-scale structure of the universe was an important milestone in our understanding of cosmic voids. These voids were not simply the absence of galaxies, but integral parts of the cosmic fabric. Now that we've traversed the cosmic maze leading to the discovery of voids, let us delve into one of the most mysterious voids confirmed to date, a void so large that it's been nicknamed the Great Void. Welcome to the Buddhist Void, named after the constellation in which it is located. The Void of Bodeus, discovered by astronomer Robert Kirchner and his team in 1981, is one of the largest known voids in the universe. How big is it? For comparison, the diameter of this void is about 330 million light years. If you were traveling at the speed of light, it would take you 330 million years to cross it. That's just from one side to the other. That's about 23 times the size of our own Milky Way galaxy. Bodeus Void is not only large, but also incredibly empty. In an area of space where we normally expect to find 10,000 galaxies, there are only 60 in the Bodeus Void. Think of it as a cosmic desert, a vast expanse of emptiness amid a densely populated cosmos filled with galaxies. The presence of such a colossal void contradicts the cosmological principle, which states that when viewed on a large enough scale, the universe should appear approximately the same in all directions. The mysteries of Bodeus Void are not limited to its size and emptiness. For example, some of the galaxies inhabiting the void are bizarrely arranged in tubular structure, and this feature is not yet fully explained. As we continue our journey through the cosmic seas, our next stop will be another prominent void, which has earned the impressive name supervoid. This is the Eridanus supervoid. The Eridanus superhollow, named after the constellation in which it's observed, is not just a void but a superhollow. It's one of the largest structures ever discovered in the universe. Just to give you an idea of the scale, this superhollow extends about 1 billion light years across. If you're traveling at the speed of light, it would take you a staggering 1 billion years to cross it from one side to the other. Eridanus supervoid is not only huge, but also incredibly barren. Although it's not as devoid of galaxies as the Bodeus Void, its vast space is still strikingly barren compared to the galaxy-rich cosmos around it. But what makes Eridanus supervoid particularly intriguing is not just its size or emptiness. This supervoid is related to a mysterious cosmic phenomenon known as the cold spot of relic radiation. A cold spot of relic radiation is an unusually cold region in the cosmic microwave background, the afterglow of the Big Bang. Some scientists speculate that this cold spot could be the result of the Eridanus supervoid. The huge void could cause a phenomenon known as the Sachs-Wolf effect, where photons lose energy as they pass through the void, resulting in a colder patch of relic radiation. As we continue our journey through the cosmic deserts, we encounter yet another mysterious expanse of emptiness. Welcome to Venatici supervoid. This supervoid, located in the constellation of the Hound Dogs, is a compelling illustration of the scale and vastness of our universe. Venatici supervoid, like its counterparts, is in a region of space with significantly fewer galaxies than expected. To understand the scale of this superhollow, consider this. It's an incredible 1.2 billion light-years in diameter. That's about 8 times the size of our Milky Way galaxy. Traveling at the speed of light, it would take you more than 1 billion years to traverse it from one end to the other. Like a cosmic desert among the lush forest of galaxies, the Hound Dog supervoid is an area of deep emptiness. While the size and emptiness of Venatici supervoid are fascinating, the question remains: how did such a massive void form? What process in the early universe could have led to such a vast expanse of void? Although the exact process that led to the formation of voids are still unresolved, several convincing theories have been proposed. The first potential scenario involves the concept of cosmic inflation. It's believed that shortly after the Big Bang, the universe underwent rapid expansion or inflation, which stretched space itself. Quantum fluctuations during this inflationary period may have intensified on a cosmic scale, leading to denser regions and less dense regions of space. Over billions of years, matter gravitated toward denser regions, forming galactic clusters and filaments, and leaving behind less dense regions that became cosmic voids. The second theory has to do with dark energy, a mysterious force that causes the universe to accelerate. Dark energy may have played a role in the formation of voids, pushing galaxies from less dense regions to denser ones, effectively inflating these voids over time. Finally, the formation of cosmic voids may also be related to large-scale structural processes in the universe. As matter and the universe clump together under its own gravity, forming structures such as galaxies and galaxy clusters, voids naturally formed in the remaining spaces. This process is similar to the formation of bubbles in a loaf of bread as it rises and bakes. Just as the dough forms solid structures around air pockets, the universe forms structures of matter around the space of emptiness. These are just some of the theories scientists are exploring to explain the formation of these cosmic anomalies. But as vast and mysterious as these great voids are, they're just a piece of a complex cosmic puzzle that scientists have yet to piece together. The exact processes that lead to the formation of voids are shrouded in mystery, and uncovering them is a daunting task. One of the main problems is the scale and complexity of the universe. The universe is vast and filled with countless galaxies, each with its own unique properties. Understanding how these galaxies interact and how they affect the larger cosmic structure is a Herculean task. Another difficulty is the elusive nature of dark matter and dark energy. These invisible forces are thought to play a crucial role in shaping cosmic structures and voids. Yet our understanding of them is still in its infancy. Without a clear understanding of what dark matter and dark energy actually are, understanding their influence on a void formation remains a considerable challenge. Despite these obstacles, current research in this field is dynamic and constantly evolving. Scientists are using increasingly sophisticated tools and techniques, from advanced telescopes to sophisticated computer simulations, to explore the mysteries of the great empties. Large surveys, such as the Sloan Digital Sky Survey, display the distribution of galaxies throughout the universe, providing invaluable data for studying cosmic voids. Meanwhile, computer simulations allow us to recreate the evolution of the universe under different conditions, helping to test theories of void formation. In the quest to understand the origin of these vast cosmic voids, each new discovery, each piece of data, brings us one step closer to understanding the truth. The great voids have profound implications for cosmology and our understanding of the universe and its structure. First, they present a unique perspective on the role of dark matter and dark energy, two elusive but dominant components of our universe. Dark matter, although invisible, is the basis of the large-scale structure of the universe. Its gravitational pull helps form the cosmic web of galaxies and voids. The very existence of these vast voids suggests that dark matter played a key role in shaping the universe we observe today. Meanwhile, dark energy, the mysterious force governing the accelerated expansion of the universe, may also play a crucial role in the growth of these voids. By pushing galaxies away from less dense regions, dark energy can inflate these voids on cosmic timescales. But the implications of cosmic voids extend even further. The study of these voids can provide important information that can help refine our current cosmological models and theories. For example, the size and distribution of cosmic voids can be a unique test of cosmological models. If a model can accurately predict the properties of these voids, this confirms its accuracy. Conversely, any discrepancies between model predictions and observations may signal the need to refine or even develop a new theory of physics. In fact, these great cosmic voids, once thought of as mere empty spaces, have taken not the least place in our quest to understand the universe. But what if these voids are more than just empty space? Their study has spawned theories beyond our familiar universe, bordering on the realms of the speculative and the extraordinary. One such theory includes the concept of alternate universes or multiverse. This is the idea that our universe may not be the only one, but rather one of many universes existing in parallel to each other. According to some theorists, the great empties could potentially be more than just vast spaces of emptiness. In fact, they could be interfaces or gateways to these alternative universes. This assumption is rooted in certain interpretations of quantum mechanics and string theory, which postulate the existence of other dimensions besides the three spatial dimensions and one temporal dimension that we encounter. If these dimensions exist, they could potentially contain many alternative universes, each with its own set of physical laws and properties. In this context, the great empties may be areas where our familiar four-dimensional universe thins and gives way to these other dimensions. It's important to note, however, that this idea is highly speculative. Although it offers intriguing perspective and has inspired countless science fiction stories, it's far from being accepted by the mainstream scientific community. To date, we have no concrete evidence for the existence of alternate universes or other dimensions. Moving on, we encounter the previously mentioned idea, the idea that unites the immensity of the universe with the infinitesimal quantum world. This concept is nothing but quantum fluctuations. In a quantum sphere, particles and energy constantly appear and disappear, creating a frothy sea of fluctuations. But what do these microscopic phenomena have to do with giant cosmic voids? The answer goes back to the earliest stages of the development of the universe shortly after the Big Bang. During this period, the universe was extremely small and hot, and in such state, quantum effects could have a significant impact on the cosmic scale. Quantum fluctuations occurring at this time may have intensified as the universe expanded. These amplified quantum fluctuations could lead to an uneven distribution of matter and energy. Regions of lower density could, over billions of years, become the vast cosmic voids we see today. In this scenario, the great voids are like ancient imprints engraved on the fabric of the universe by quantum fluctuations in the earliest moments of its existence. It is important to note, however, that while this theory is intriguing and has some basis in our current understanding of physics, it still remains a hypothesis. Verifying such a theory is a difficult task that requires accurate measurements of the large-scale structure of the universe, as well as a deeper understanding of quantum physics and cosmology. Nevertheless, the prospect of connecting the realm of the quantum with the cosmic, the smallest scale with the largest, is tempting. Another fascinating hypothesis plunges us into the complex abstract world of topology, the mathematical study of space and its properties. In the context of the universe, topological anomalies or space defects refer to irregularities in the fabric of space-time. Just like fabric defects, these defects may represent areas where the normal structure of space-time is disturbed. But where could these anomalies have come from? To answer this question, we have to go back to the inflationary period of the universe, a fraction of a second after the Big Bang. During this ultra-fast expansion phase, the universe grew exponentially. Although this inflation smoothed the overall distribution of matter and energy, it may also have exaggerated tiny irregularities in the fabric of space-time, causing topological defects. These defects could then act as a place around which matter could not easily accumulate, eventually leading to the vast empty spaces we know as cosmic voids. The study of cosmic voids would not be complete without the study of one of the most mysterious objects in the universe, black holes. Specifically, we're talking about primary black holes. Unlike the black holes we're familiar with, which form as a result of the collapse of massive stars, primary black holes are assumed to have formed shortly after the Big Bang. They may have been created by extreme density fluctuations in the early universe. Now, you may wonder, what do these ancient black holes have to do with our great cosmic voids? Well, one claim suggests that these voids may be teeming with primary black holes. According to this idea, the large void may be the result of a large number of primary black holes hiding in these regions. Since they do not emit significant radiation, they would be difficult to detect directly. Their presence, however, will have a gravitational effect, effectively clearing their surroundings and contributing to the enormous void we observe in the cosmic world. Another theory intertwines the story of the emergence of the great voids with the elusive dark matter. Dark matter, although undetectable by conventional means, is thought to make up about 85% of the universe's matter. It plays a crucial role in the formation of cosmic structures, weaving a vast, entangled network linking galaxies together. These strands of dark matter, known as filaments, serve as supports for the universe, guiding the formation of galaxies and galaxy clusters. But what if something were to break these threads? What if a massive event or unknown force could cause these threads to collapse or disintegrate? That is where cosmic voids come into play. According to this theory, the collapse of strands of dark matter could lead to the formation of these huge voids. The collapse of these filaments would disrupt the flow of matter, leaving behind vast, empty expanses. So, as we've already understood, these vast expanses of emptiness are quite far from being barren wastelands. They are a treasure trove of clues and mysteries about the universe and its composition. From the formation of the large-scale structure of the universe to the behavior of dark matter and dark energy, the mystery of the great void forces us to rethink our understanding of the cosmos. And while we may not yet have all the answers, every question we ask, every void we explore, brings us one step closer to unlocking the mysteries of the cosmos. And remember, every time you look up into the night sky, you see not only stars and galaxies, but also invisible cosmic voids.
These silent guardians of the cosmos continue their eternal vigil, keeping the secrets of the universe in their vast expanses.
Our planet appears as a serene oasis against a vast cosmic desert. But beneath this calm facade lies a dynamic force, invisible but powerful, constantly shaping our world in invisible ways. For millennia, mankind has looked to the stars to find their way, unaware that an invisible guide silently guided them. This guide, the Earth's magnetic field, an invisible shield, was our silent protector, shielding us from the merciless solar winds and cosmic radiations. But what if this constant of our lives was on the verge of a colossal change? A change is so profound that it could change the way we live our lives. Deep beneath our feet, in the heart of our planet, lies the key to this mystery. A restless ocean of molten iron is churning, creating a magnetic force that envelops our world. But this force is not as constant as we once thought. Scientists have unearthed evidence hidden in the very bowels of our planet that tells the story of an ever-changing world, of flipping poles, changing the direction of the magnetic field, and turning the world as we know it upside down. This is the story of Earth's geomagnetic inversions, a phenomenon as mysterious as it is fascinating. Our story begins with an invisible force that has imperceptibly changed the course of our planet's history. That force is the Earth's magnetic field, a complex and dynamic energy that extends far beyond the planet's surface into the space around us. Since ancient times, this magnetic field has been a silent guide for explorers and mariners, leading them through uncharted waters. It is a force so subtle that it goes unnoticed, yet so powerful that it has played an important part in the survival and development of civilizations. Deep inside the Earth is the heart of this magnetic force. Here, in the outer core, a bubbling ocean of molten iron generates the magnetic field. This motion, caused by the Earth's rotation, creates the dynamo effect, a process that maintains the magnetic field for billions of years. This field is not just a landmark for navigation. It is a shield. It reflects harmful solar winds and cosmic radiation, protecting our atmosphere and ensuring the survival of life on Earth. But this guardian is not as unchanging as it seems. Throughout Earth's history, the magnetic field has undergone dramatic transformations, geomagnetic inversions. These are periods when the magnetic poles change, north becoming south, and vice versa. Evidence of these changes is captured in the very stones of our planet. As volcanic lava cools and hardens, the minerals within it align within the Earth's magnetic field at the time. By studying such rocks, scientists have discovered that our planet has undergone many changes. These changes do not happen suddenly. They occur over millennia. The field weakens, becomes chaotic, and gradually restores the opposite orientation. The reason for these changes remain one of the greatest mysteries of geoscience. As we delve deeper into this mystery, we begin to realize the immense power and fragility of this invisible shield. The history of the Earth's magnetic field is a story of constant change, a reminder of the dynamic nature of our planet. As we delve into the past to unlock the mysteries of geomagnetic inversions, we turn to the Earth itself, our most reliable historian. The geologic record contains evidence of these monumental shifts. Volcanic rocks, especially basalt, have become invaluable in this kind of research. As we mentioned, as the lava cools and hardens, the tiny magnetic minerals within it align with the Earth's magnetic field. This natural recording process created a timeline of the Earth's magnetic history locked within these ancient rocks. While studying these rocks, geologists discovered a startling fact. Over the last billion years, the Earth's magnetic field has reversed hundreds of times. The most recent of these reversals, the Bruns-Matayama reversal, occurred about 781,000 years ago. These reversals are irregular and unpredictable, with intervals ranging from tens of thousands to millions of years. This process is gradual and takes thousands of years. Another piece of evidence comes from the ocean floor. Here, magnetic striping, bands of rock with alternating magnetic orientation, coincide with mid-ocean ridges. As new rocks form and spread out from these ridges, they record the current orientation of the magnetic field, creating a symmetrical pattern of these reversals on either side of the ridge. Scientists have recently observed changes that hint at a potential upcoming reversal. Satellites and observatories have detected a gradual weakening of the magnetic field and increased movement of the North Magnetic Pole. The magnetic North Pole, once firmly established in the Canadian Arctic, is now drifting with acceleration toward Siberia. This movement, although not a definitive sign of an imminent reversal, is a clear indication of the dynamic nature of the magnetic field. Other indications include the development of the South Atlantic anomaly, an area where Earth's magnetic field is much weaker. This anomaly grew and deepened over time, affecting satellites and spacecraft. As we piece together these clues from the past and present, the history of geomagnetic inversions becomes clearer. These historical and contemporary observations not only reveal the dynamic nature of our planet's magnetic field, but also remind us of the ever-changing nature of the world in which we live. To understand the mechanics of geomagnetic inversions, we must travel deep into the heart of the planet, to a place where intense heat and pressure produce one of the most mysterious phenomena on Earth. A core located at the center of the Earth is divided into two parts, a solid inner core and a liquid outer core. The outer core, consisting mainly of iron and nickel, is in constant motion due to Earth's rotation and thermal convection. The movement of liquid metal generates electric currents, which in turn create magnetic fields. This process, known as geodynamo, is the driving force behind Earth's magnetic field. The dynamics of the outer core are complex and not fully understood. However, scientists believe that the Coriolis effect, a consequence of the Earth's rotation, plays a decisive role in the configuration of the magnetic field. The Coriolis effect causes convection currents in the outer core to spiral, creating swirling vortices. These vortices are thought to organize magnetic field lines, keeping the magnetic poles aligned. But what happens during a geomagnetic reversal? Current scientific understanding suggests that these reversals begin with a weakening of the magnetic field. This weakening can disrupt the alignment of the force lines, making them unstable and chaotic. As the field is weakened, the influence of the Coriolis effect on the motion of the outer core decreases. This reduction in influence allows the magnetic field lines to realign in the opposite orientation, effectively reversing the poles. But let's consider the Earth's magnetic field not only as a compass reference point, but also a vital protector. The invisible shield, built deep inside the planet, is our first line of defense against harsh solar radiation and cosmic threats. The Sun, a fiery cauldron of nuclear reactions, constantly emits solar winds, streams of charged particles that can be devastating to life and technology. However, the Earth's field deflects these particles, creating a safe harbor for life to flourish. This magnetic shield also protects us from cosmic rays, high-energy particles, distant supernovae, and other cosmic events. Without such protection, these rays could pose a serious threat to humanity's biological systems and electronic infrastructure. However, during a geomagnetic field inversion, this protective shield is significantly weakened. This weakening can lead to an increase in the radiation impact on the Earth's surface. The potential consequences of such increased radiation are profound. It can affect climatic conditions, potentially lead to dramatic changes in weather. Elevated radiation can also have biological consequences, affecting everything from human health to the behavior of animals, especially those that use magnetic fields to navigate. Moreover, a weakened magnetic field could leave our technology vulnerable. Satellites, power grids, and communication systems could be jeopardized by increased solar and cosmic radiation. These simulations show that the magnetic field is in turmoil, with multiple poles appearing and disappearing and magnetic lines of force moving and changing in a complex pattern. This study of the Earth's magnetic field as a dynamic protector not only highlights its importance, but also emphasizes the need to understand and prepare for potential problems resulting from its weakening during a geomagnetic reversal. What about the potential global implications of a geomagnetic reversal and humanity's preparedness for such an event? This phenomenon, although a natural part of the Earth's geological cycle, poses serious challenges in our technologically oriented world. On the one hand, geologists discuss the likelihood of such an event, emphasizing its inevitability given Earth's history. However, scientists express concern about the vulnerability of our satellite networks, power grids, and communication systems. A weakened magnetic field could lead to increased solar radiation, potentially disrupting such critical technologies. Also, let's not forget about possible climate change. Although the exact effects are unknown, some models suggest that shifts in the magnetic field could affect weather patterns, potentially leading to extreme and unpredictable weather patterns. One thing is certain: the impact on wildlife, especially migratory species like birds and marine animals that use magnetic fields for navigation, and that could be catastrophic. Disturbances can lead to ecological imbalances and affect biodiversity. Research aimed at understanding and predicting the timing and consequences for geomagnetic reversals is ongoing. The need for global cooperation in such research is key to developing strategies to mitigate potential risk. It is a reminder that while we may not be able to prevent natural events of this magnitude, through understanding and preparation, we can mitigate their impacts. As we near the end of our journey, we turn our attention to the future, specifically how scientists are tracking and predicting changes in the Earth's magnetic field. At the forefront of this research is a fleet of sophisticated satellites equipped with instruments capable of measuring all the subtleties of the magnetic field with unprecedented precision. Projects such as the European Space Agency's SWARM mission provide valuable data on magnetic field strength, direction, and anomalies. These satellites are complemented by a network of ground-based observatories that continuously monitor the magnetic field at various points on the Earth's surface. Together, these instruments offer a comprehensive view of the behavior of the magnetic field and its variations over time. The data collected are not just for scientific curiosity. They play a crucial role in predicting the future of the Earth's magnetic field. By understanding the patterns and causes of past geomagnetic reversals, scientists hope to better predict when the next reversal might occur. While the exact consequences of a future reversal are still a matter of research and debate, the consensus is clear. Understanding and preparing for such an event is crucial. This involves not only scientific research, but also public awareness and international cooperation. Just as we've overcome the challenges of our past, we're ready to face the future with knowledge, technology, and a spirit of cooperation. The study of the Earth's magnetic field From its historical changes to cutting-edge research aimed at understanding its future, emphasizes the interconnectedness of science, technology, and society. It's a reminder of our place in the vast cosmos, with the ongoing need to understand and respect the forces that shape our world.